Yeah, maybe time based on basically
So I realized this was an ambitious lecture and it's early in the morning, so I'm just going to cut it back a little bit. I just want to do two things, and then we continue the break. I want to state and give a hint, but I won't do any of the math. This is the lecture notes. I think this is interesting for some people. It involves some representation theory, and so if you like that kind of thing, you should look up the notes. I just want to make the statement to clarify the point that Tower raised about the degrees of freedom. Also, because it's a powerful statement about the decision inequality, so I state it and say just one word about how you prove it. That will take us 10 minutes. And then the remaining 5 or 10 minutes, because I think it's very fun and it answers some of the questions, I want to tell you what this magic square game is that I mentioned earlier. It's a different game, and it's a fun game. So we do first the hard part and then the fun part. So first I want to state this CHSH theorem. So let me state it. And it's not that bad. So the theorem says the following. It says, suppose that I have a good strategy in the CHSH theorem. So strategy is the state, right? And that state is a state that's going to be split between Alice and Bob. There's a bunch of qubits, so that some state. And then some observables for Alice, and some observables for Bob. Such that the value that these guys, the bias that these guys achieve in the CHSH game, so I write it in this way, so it's just whatever this strategy does in the CHSH game, is almost the optimum. So it's at most the optimum we saw was 1 by root 2, and it's almost that, but it's not quite. So for some epsilon. Okay. What's relevant about this is that it's experimentally accessible quantity, right? I can have two persons who claim they're Alice and Bob, and they claim they can play well in CHSH. I can test that. I don't myself don't need to do anything quantum. I'm just going to ask them these questions, check the answers, repeat it many times, average out how many times they succeed, and if the average is of the biases is at least this, I say good, right? That's why I need the epsilon, because if I didn't put an epsilon, they're never going to do exactly the right thing, right? There's always a little bit of error, and there's some statistical fluctuations. It would be unreasonable to ask that you do the exact thing. So that's why. What's the conclusion? Then what? Then there exists two things that are local degrees of freedom. So then there exists, they're called local isometries, but think of them as just local rotations. Okay, so a change of basis. There's one for Alice. So it goes from Alice's space into the space of a qubit, tensor some other stuff. And another one for Bob that goes from Bob's space into the space of a qubit, tensor some other stuff. Such that the following is true. And what's true is that, first of all, if I apply these rotations to the state, that was just some arbitrary state, right? Anything. I apply the rotations to it, so VA tensor VB, a change of basis. Then what do I get? I get something that looks like the EPR state. Let me call it EPR prime. It's the one that we had for the strategy. So EPR prime on AB, so that's AB, tensored with some other state, arbitrary state, A prime, B prime. So I could already stop the theorem here. It would be a strong theorem. This theorem is saying, look, you've been using a state and observables. I don't know what they are, but I've observed that when I play the CHSH game with you, you do really well. Then I know that up to some rotation locally on Alice and Bob, that is not something that I can control, then the state that you've been sharing is equivalent, up to a little error margin that's related to my error there, to an EPR state. It's the EPR state. Tensor some other stuff, right? Because maybe you have some other stuff. I mean, what do I know? I don't know if maybe you have 10 EPR states, right? That's fine. What this is saying is that you have at least one, and it's here. I can find it just by doing local rotations in the state. Because local rotations don't change the amount.
It should be HP prime.
Oh yeah. Okay, so that's the first point. And that was shown already by Reinhard Werner and someone Summers in the 80s. It's something more, a bit more recent with a words bound. So these kinds of theorems are actually have only been refined in the past few years. It's pretty recent. And then the other is saying that not only I know the state, but I know the operations. In what sense? So I know that the state is psi, right? And one thing that could happen to psi is that Alice applies the observable A0. Right? So this thing could happen. And then I have to apply my middle rotations afterwards. These are just my changes of basis. But then I know that this is the same as Z for Alice, tensor identity, applied to the DPR prime. Okay, and I could write the same line for each of the four observables. I'm not going to do it, but what this says is that, again, up to just a choice of a basis, right? There's this degree of freedom, you have to choose a basis, fine, but up to a choice of basis, when Alice applies the observable A0 to psi, what she's doing is she's really applying a Z observable to her half, so this is the identity of B, of the EPR. This is very nice, because now I know that if I tell Alice the question 0 in the CHSH game, she applies a Z operator on an EPR pair. I know it. Otherwise, she's going to fail in the game. So that gives me a very strong handle on the operations that are happening in Alice's space, even though the only thing that I ever observed about her are classical data, right? I mean, I sent classical questions in the CHSH game, I got classical answers. I computed some statistics, some classical statistics, and suddenly I know exactly what her system is. It's a half an EPR pair, and what her operations are. That's the statement of the theorem. Is that a question, Charles? Just scratching it. Okay, how do we prove this? So this is the part that I'm not going to do. I'm not even sure I need the word. The proofs are interesting though. There's two steps in how you prove that. And the first step is to rewrite the assumption, what does it mean for you to succeed well? And rewrite this as algebraic conditions of the observables. So the first step is going to say that if you do well, this implies conditions that look something like this. They look something like A0, A1 plus A1, A0. So that's the anti-commutator. Okay. And I look at the square norm of this anti-commutator of the state. This has to be small. Okay. So this is just by, you play around with the expression for the CHSH game and you realize the only way to do well in that game is that Alice needs to use two observables that basically anti-commute, right? So if they anti-commuted, this would be minus that, I would get 0. This is saying that they approximate. So you work a little bit, you get there. Same for Bob, things that approximate. So the example, the observables that anti-commute are X and Z, right? So our strategy for the CHSH had worked well. It had XZ plus ZX. ZX is minus XZ, I get 0, so this is satisfied, right? So this is saying that whatever you do, they must approximate. Yeah.
So if they're isometries, do they have a component of translation in addition to the rotation? Because strictly speaking, from a differential geometric perspective, they can. I'm just wondering.
No, they're linear maps. They're not that fine. They're linear maps.
Okay, because otherwise it would be very hard to bound to the let's say good epsilon if the translation.
Yeah. No, there's no translation. It's not. I said rotations, but that was a really loose analogy. They're really. You think of them as unitaries, but they can embed in a larger space. You should really think of them as unitaries. And the second part is to argue that basically you're done. So any operators that approximately anti-commute must be equivalent up to a change of basis to X and Z. So you have that A0 is approximately equivalent up to conjugation by this V, and so the way I wrote it is So up to a change of basis, VP dagger, this should be approximately equal to X, and A1 up to a change of basis should be approximately equal to Z. And then you're done. Once you know what the operators for Alice are, X and Z, and for Bob you do the same thing, then you get all the components of the theorem.
Right. Even stronger statement, no? You get even stronger statement, and second, you get also that A1 should be Z.
Yeah, I didn't write it, but it's also the case. It is the case. Yeah.
You can.
Did I get the wrong? Oh yeah. Sorry, thanks. Yeah. So that is a bit of a sloppy statement. One thing that's worth pointing out about this here is I'm saying it's strong. You have to be a little bit careful in what it's actually saying. And one thing that it's not saying is that exactly what I wrote there. It's not saying that just as matrices, these guys need to be approximately the same. It's only talking about the distance between the operators when you apply them to the state. And that's because that's the only thing that's observable. I don't know how these operators look like in portions of space that are not being used, or that have other states, or that are not relevant to the game. So I can only make statements about how they look like on the state, not as operators. And so that is kind of nice, just the point of view of the math. So this is what I mentioned. If anyone likes representation theory, the idea in order to go from here is to interpret these operators as an approximate representation of a certain group that's related to the volume group. And then use theorems that say that approximate representations, which is this, are close to exact representations. And exact representations of the volume group are just pointers. I just put the buzzwords in case anyone likes it, but that's what I'm going to say. Okay, so that's what I wanted to say about the theorem. Any other questions about it? Okay, so that's it for the game. That's it for the game. So this game is nice. Why? Because so a few people asked the question about how well can quantum players do than classical players in the game. Can the quantum players win with quality 1 when the classical players cannot? Does that have consequences for complexity theory, etc.? And that's a question that I cannot answer using XOR games, but that I can answer using this example with the magic square game. So it's a very simple game. It's not much more complicated than the CHSL game. So I'm just going to describe it. So the game is parameterized by a square. Think of it as a magic square. So it's think of it just as a square. So it's a 999 square. Looks like this. And then there's conditions on that square, which is that I'm going to have to fill in the entries of the square using values 0 or 1, such that certain parity conditions are satisfied. So actually, let me describe the game. Sorry. So the square is just something in your head. Okay? But what's the game? There's Alice and Bob, and there's the referee. And the referee is going to choose one row or column and ask Alice about it. Right? So we send her something like either row number 2 or column number 3. And she has to reply with values that fit in this row, for example, the second row. So she'd say something like 0, 1, 1. So that's 3 bits, A prime, A double prime. And the condition is a condition on the parity. So for example, if I ask her for this row, then the parity of these entries should be 0. Here the parity should be 0. Here the parity should be 0. The parity should be 1. The parity should be 1. So for the rows, the parity should be 1, and for the columns, the parity should be 0. Okay. So for example, that's a valid answer for Alice. I asked her about the row. She gave me these. The parity is 0. Check. Alice is fine. If I had asked her for maybe the second column, then that's good. Okay, that's good because the parity is 1. Another one that's good is this. That's good. The parity is 1. So that's the answer for Alice. Okay, so what about Bob? Bob, I'm going to ask him. So I asked Alice, for example, column number 2. I'm going to ask for Bob just one of the squares in the column, and I also ask him for a value. Right? So for example, I'll ask him for the square, let's say the bottom one. So let's call it square sub, third row and second column. Okay? So I just tell him this, and he has to send me a value b. And let's have Bob in blue. Blue is going to tell me, for example, 1. And it's as earlier for the clause variable game. They have to give me the same answer. That's the game. Does it make sense? So I choose one row or column at random. For example, the second column, ask Alice about it. She has to give me values. and then Bob, I just wanted the square. So I want to make two claims about this game. One is that you cannot win classically with probability 1 in this game. The best you can do is, for this version, 17 by 8. So close to 1. Okay, how do I see this? So we have to think of let's try to figure out a strategy. I mean, how do we go about finding a strategy that always wins, right? So we have to find a strategy for Bob and then for Alice. So what's the strategy for Bob? Okay, Bob gets asked for a square, so we have 9 possible questions, and he gets to assign a value to the square. So we could list it, right? So a strategy for Bob is something like, so far there's not really any conditions, so I could say, okay, Bob 1, 0, 1, 0, 0, 1, 1, 0, 1. I just put random things, right? That's just any strategy for Bob, it looks like this, it's just values. Now I have to write a strategy for Alice. The strategy for Alice is a bit more tricky, because for each row and column, I have to write something, right? Now if I want them to win with certainty, it should be the case that whenever Alice writes something in the column, like for example, I'm going to write answers for her in that column, let's say 0, 1, 0. From Alice's point of view, if she's asked this column, there's always a chance I could ask Bob about this square, or that square, or that square. But Bob, we decided what he says, right? If he says this square, he says 1, this square, 1, this square, 1. So if that's Alice's strategy for this column, it's not going to work. Because only if I happen to be lucky and ask Bob for this entry, they're going to match, but the others don't match. So Bob's strategy, if I want him to win all the time, Bob's strategy forces Alice to say the exact same thing. She has to say this in that column. If she doesn't, for example, if she says this, there's a chance. I'm going to ask her for that column, and Bob that entry, and then this thing. So it's moving. Does that make sense? So Bob's strategy is just a value for each square, but then once I've said that, because I always ask them to be consistent, and because Alice doesn't know when she's asked a column or a row which square I'm going to check her against with Bob, she just has to say the same thing as Bob, otherwise there's a chance. And I want them to win those. Okay. So same for the first row. Alice has to say the same as Bob, and there's no choice. She has to say the same as Bob, she has to say the same as Bob. So we can sort of forget about the fact that there were 2 players right now, and or we can forget about Bob, and then try to come up with a strategy for Alice or Bob at the same time, which is just we need to fill in all the entries in just a single way, which is Bob's way, but Alice has to do the same thing. Okay, but Alice has more constraints, right? Alice has to satisfy these priority constraints. So I went too fast, and probably this is not going to work out, right? Because, okay, this, for example, this is no good. Because if Alice is asked for the third row, 1 plus 1 plus 1 is 1, it's not 0, right? So that's not good. Okay, so I need to fill in the square by rows and columns such that all the constraints are satisfied. Okay, at least one person is smiling, maybe more. So, okay. It's going to be hard, right? Can someone say why it's going to be hard?
You can do it.
I can't? You can't? Cannot?
Cannot.
Who's speaking?
At least one square must be wrong, right?
Yeah, what?
Some of the all entries.
Sorry?
Some
Right.
of all the entries.
His point is that I can't do everything. Why cannot do everything? Let's just take the parity of everyone, right? And let's take the parity row by row. Then I should get parity 0 plus 0 plus 0. Total parity should be 0. Okay, fine. Let's take the parity column by column. 1 plus 1 plus 1, 1. The total parity should be 1. My constraints are just, they're self-contradictory. This is just impossible, right? So you can't win this game with one. And yeah.
So this is the theorem mentioned earlier, like you pick an arbitrary clause, right?
Yeah.
And because this cannot be satisfied, so there's no
Exactly. Yeah, very good point. So this is a special case of the clause versus variable game, right? So you can think of these, they're not three-stat constraints, they're XOR constraints. I could make them into three-stat constraints, but it doesn't matter. Think of it as a formula. It's a formula that has 6 clauses, and these clauses say that parity of x1 plus x2 plus x3 should be 0, 4 plus 5 plus 6 should be 0, etc. Right? So there's these 6 clauses, and again I choose a clause at random, which is just a row or a column. I ask Alice about the satisfying sign of the clause, involve one of the variables, and they should be consistent. And the formula is not satisfiable. I can't solve this square thing, and so there's no.
And if the formula was satisfiable, then they just agree on the satisfying assignment.
Yeah, and then they would. But in that case, it's not. And so what's amazing, so that is saying that, okay, if I look at the maximum success probability of players for this magic square game, divided MS, they must fail in at least one question and there's 6 times 3 questions, 18, so it's at most 17 over 18. Doesn't matter exactly. So what's amazing is that even though this is impossible, right? I mean, we all checked it together. You cannot win in this game. Right? The quantum layers, so the quantum value of the game, this is 1. So there's a quantum strategy for the players. Whatever question you ask those guys is going to be the correct answer. Always. Why is this possible? And that's crazy, right? Because you can't. The reason is that the quantum guys, I can't do this reasoning, right? This reasoning was based on saying, let's write down what Bob's strategy is. Bob's strategy is an entry for each square. Okay, let's try to do this in the quantum case. Right? Okay. Bob's strategy is like half of an entangled state and measurements on that state. And so his answer to the first square is, okay, I can sort of figure it out, right? I make the measurement, I get an outcome. But once I've made the measurement and given the outcome and figured out what is Bob's answer here, I messed up the state. The state is destroyed. Alice's part is still there, but Bob's state is destroyed. And so it doesn't mean anything to make the measurement here and again and ask, what if Bob answers, what is Bob's answer here and Bob's answer there? I can't answer that question. The measurements are incompatible, I can't make that answer. What's very nice is that if you look a little bit more closely what happens, what are these observables? I'm not going to tell you, but they're simple. This strategy uses 2 EPR states, the same as before, and the measurements that Alice and Bob make, so each of them has 2 qubits now, and they just make simple, like, Pauli XNT measurements. I'll just say one last thing that I find very clear about this game. Why is this possible? What is going on? If you think about, this is a bit of a high-level comment, if you think about Bob's strategy in the game, right, it's just its values. So I could write, this is like the clause versus variable game, and so Bob has a certain value for this square, x1, and a certain value for this square, x2, x3, x4, or sorry, whatever, 4, 5, 6, x6, okay? And so the reason this didn't work, was impossible in the classical case, is that there's no assignment plus minus 1 to these variables that satisfies all the constraints. Why? Because I can multiply all the variables in one way, or in another way, and in one way I should get plus 1, in another way, well, if they're plus minus 1 variables, in one way I should get minus 1, in the other I should get plus 1, and minus 1 is different from 1, and so this is impossible. The difference with the quantum strategy is that you have to do a little bit more to see this, so I'm just saying at a high level. The quantum strategy, to win in this game, it's an assignment not of just a plus minus 1 value to each square, but an operator, an observable. So it's a capital X1. It's a 2x2 or a 4x4 matrix. And if you allow yourself matrices, now you can solve the square. So these, if you try to find 4x4 matrices that have plus minus 1 eigenvalues, sort of the quantum generalization of the class of assignment, you can fill in the square such that all of the constraints are satisfied. And why is that possible? We don't have a contradiction as we had before, and the reason is that matrix multiplication doesn't commute. Variable real number of multiplication commutes, but not matrices. And so it's fine to have 9 matrices such that if I multiply them in that order, I get the identity matrix, but in that order, I get minus the identity matrix. That's not a contradiction. It's the product of the same matrices but in a different order, and I can get a different. So that's what.
My question, so the fact that the value is 1, does it mean that they don't destroy the state?
No. Because it's also the case in that strategy that the marginal distribution of outcomes that Alice and Bob did is uniformly random. So they do not give deterministic answers. They give uniformly random answers. And so it does destroy the state. If it didn't destroy the state, then it would be a classical strategy. So it can't, it's not, compared to your earlier question, it doesn't.
So it's not that the product of the matrices is 1, it is that
It is
one
one.
state.
No, it is one. It is one. Yeah. But when you're asked the question, so these are they're like this. The strategy Bob's, what are Bob's observables? There's something like X tensor identity here, so that's an observable on 2 qubits. This is the Pauli X. Here it's like identity tensor X, and here it's like X tensor X. The product should be should be 0, so it should be 1. So this is what. Then I fill in all the squares. This is what it looks like. But this is saying, for example, right, if Bob gets asked this square, he's going to measure the first qubit of the first EPR pair in the X basis. That is good. But still, the product of the 3 matrices is the identity. Yeah.
The ref can only ask of person A can only ask for 1 row or 1 column, right?
Yeah. So you change this game and say, well, what if I start asking Alan Bob for 2 squares at a time, or then you can mess up the quantum strategy. Then it's definitely, yeah.
So in that mapping, it's just instead of A prime, A double prime. Classically, you could do all that, but not.
Yeah.
I just have a question. When you multiply matrices, then what is going to be 0 and 1 in that case?
Sorry?
I understand how you can, how you get the parity when you have numbers, but I just don't know how to do it for matrices.
Yeah, so I went a little bit fast on that, so let me just take 30 seconds to answer that question, because I did 2 things at the same time. The first thing is that I was staying with variables, but instead of having these variables be 0, 1 and talking to the parity, I changed the game and I said, let's just think of them as being plus minus 1. And so in that case, my rules are that I should get plus 1, plus 1, plus 1, minus 1, minus 1, minus 1, and these are plus minus 1 values, right? So for example, something that's correct for the first row would be plus 1, minus 1, minus 1. So it's the same game, but just related stuff. That's the first thing that I said. And now, then I went a little bit at a high level. I said, look, let me tell you what is the quantum analog of this game. What's the quantum magic square? The quantum magic square is you have to fill in each of the entries by a matrix. So a 4 by 4 matrix, x1, it has to be unobservable. So permission squared by identity. Okay, it could be any dimension you want, but you need to fit it in. And what are the conditions? The conditions are that now I have matrices and a number, right? So I'm changing the condition. The condition is that the product of the 3 matrices, which is a matrix, should be equal to the identity matrix on the rows and minus the identity matrix on the columns. On top of that, for this requirement to make sense, I just ask that any row, these 3 should commute. So it doesn't matter. These 3 should commute. These 3 should commute. These 3 should commute. But it doesn't mean that everyone commutes wherever. It doesn't mean that this guy commutes with that guy. Right? And so then what I'm saying is that, well, if this is the case, then what? So this should be true. Then this should be true. And then the last one, x7, x8, x9. All these things should be true, right? If I satisfy. So then I can multiply the 3 equalities together, and I get x1, x2, x3 times x4, x5, x6 times x7, x8, x9 should be plus identity. This has to be true. Right? I can do the same for the columns. The columns would say that x1 times x4 times x7 should be minus identity. Okay? And then I take the product over the columns, and I get that what must be true is that x1 times x4 times x7 times x2 times x5 times x8 times x3 times x6 times x9 is minus identity. The same product as we had before, now it should be minus identity, but they're in a different way. And so I'm just saying it's possible. So you can write all images that you can do this. And that's sort of what explains the fact that you can do quality 1, etc. Skipping it. Yeah.
Another question. So here you wrote the conditions of a solution. Like you want like x1, x2 to be identity, and you want commute, which is maybe like x1, x2, x2 should be identity, and you want all these conditions, right?
Yeah.
So these set of conditions, they have to have a solution. In general, if I write this type of linear equations or products of matrices, do we know of an efficient way to check if there is a solution?
Theorem. It's undecidable. That's a theorem from last year. It's a hard theorem. You can embed the word problem in finitely presented groups in that question.
In that question, we write this sequence of linear equations.
Yeah, you can take any finitely presented group that satisfies some reasonable conditions, and you can construct a system of equations like this that is going to have a size that depends only on the size of the presentation of the group, such that the system is going to have a solution if and only if a certain word in the original group is triggered. So that's
This one, how lucky that we found the solution for this one.
yeah, so that's an easy one.
Could you give us a reference for this result?
I can. It's a paper by someone called Sloss. It's referenced in the lecture notes. Okay, last question, and then I think we need to break.
Is there a corresponding theorem like the CHS gene for this?
Sorry?
Is there a corresponding
Yeah, there is.
like
Actually, Janex has a paper about this, showing that also for the magic square game, there's a unique way to win it with quality 1, and it's it's whatever it is. It's these like 2 people problems. Okay, so coffee break, and then maybe we take a 20-minute break since we had a break before. We started 11:45.